In this lecture, we are investigating inferential statistics. So our lesson outline, we're going to investigate three broad areas. First, the background for our inferential statistics. We're going to link those to the descriptive statistics we used in our previous lecture. We're going to cover a lot about hypothesis testing and confidence intervals. This really is the center of understanding a lot of our inferential statistics. And then we'll highlight some of the methods of analysis at the end. I'll remind you, just like I did in our last video, for descriptive statistics, this is more like a highlight video. We got into a little bit of details of some of the computation in our descriptive statistics. We're going to do the same thing in our inferential statistics. We're going to focus most on any computational work under hypothesis testing and confidence intervals. But this is an intro to quantitative research. It's not our true introduction to statistical analysis. So we're just going to highlight those methods when we talk about t-tests or analysis of variance and regression. We're just going to highlight some of those methods. We're not getting into computations of those. But in the hypothesis testing, we're going to do a little computations. We're going to come back to the ideas in our descriptive statistics of z-tests and z-scores. So in hypothesis testing and confidence intervals, we'll do a little bit of the calculations, and that will give us our intuitions that what we're actually using in our other methods of analysis. Before you get started with the inferential statistics overview, it's very useful to make sure that you have the concepts and ideas of descriptive statistics down. So you might want to go back and review distributions of scores, recall issues of measures of central tendency, the mean, median, and mode, ideas of variability, in particular variance and the standard deviation, and our shapes of our distribution, what distributions look like, how they change. We're going to be talking a lot using the ideas of distributions and the theory behind distributions, using central tendency and variability. So we're going to use those concepts now when we get into inferential statistics. So if they're not as familiar, you can go back and review those, or you can pause at different points as we go through our inferential statistics overview and maybe go back and review some of our descriptive statistics as well. A short recap that you can also go back and review is the idea and difference between statistics and parameters. As you recall, a statistic is a value that represents the sample. It's some component of the sample that's been computed, whereas a parameter, it represents the population. So we have means of samples and means of populations. We have standard deviations of the sample and standard deviations of the population. And we started to get the intuitive feel that our statistic is our evidence for a population when we could not actually acquire data from the population. In inferential statistics, that's exactly what we're going to do. We are going to generalize from a very small group to a much larger group. Our descriptive measures of the population, our parameters, often cannot be computed directly. Very rarely are we actually able to get the entire population information and calculate out a mean. So instead, we use our sample data, our statistic, and from that sample, we make inferences regarding the population parameter. The idea of drawing inference, to draw a conclusion based on evidence and reasoning, is what we're doing in inferential statistics. That's different than descriptive statistics. We're going to focus a little bit on some hypothesis testing ideas, and I'll discuss some issues around effect sizes. We'll get into some of the classical issues around hypothesis testing, as much of our analyses are related to the idea of testing things like we'll discuss as a null hypothesis or alternative hypothesis. Inferential statistics is a conceptually sound process for making inference, for drawing inference. The very general idea of making an inference from statistics to parameters is focused on obtaining the sampling distribution, which use statistical techniques to make an inference about the population. So you can think of it, we compute a statistic from the sample data. So we gather data, we compute a statistic, and then we use those measures to generalize to the population. We are drawing conclusions about an underlying population based on a sample, or you can think of it as a subset of the data. So your population is all possible values that you might be interested in, and we're going to gather a subset of that data. And again, the reason why is in most cases, if not all cases, it is not practical to obtain all of the measures of a given population. Whatever that population is, to have it, you'd have to get the measurement for it, you'd have to have all possible values. So especially when you start thinking about surveying or conducting analysis, like my simple idea of seeing whether or not healthy eating, healthy snacks impacts performance on a math assessment. If I wanted to draw a conclusion about that, draw inference about that, I can gather a sample of some students, maybe in 7th grade, and gather a subset of the data, do a comparison study, a treatment control group, very simple model, and draw a conclusion from that data. To get a parameter estimate for 7th grade students in mathematics courses, I'd have to get all the data from everyone in the United States that's in 7th grade. Of course, that's not going to happen. So, and even if I were to do a subset, say just one state, Maryland or Virginia, or even a county, one county in a state, of New Jersey, Virginia, Maryland, even in DC, a district. And sometimes even in a school, it is very difficult to get an entire population value. So we use sampling, and we use good sampling techniques, and we draw conclusions using statistical inference. Inferential statistics is based on probability theory and distributions related to those probabilities. We use probabilistic thinking, we use probabilistic reasoning, and the idea of underlying distributions or distribution theory. So in statistical inference, we build this process of using a data analysis to infer something, to suggest properties of some underlying distribution that might be connected to our population. So in inferential statistical analysis, we infer properties of the population from the sample that we have. And we're going to use tests. We're going to test some hypotheses and derive some estimates to do so. We make a really strong assumption that the observed data that we have is part of the larger population, has been sampled from the larger population. Random sampling is back. We want to sample data that we have available. It should reflect what the population would look like within some random sampling fluctuation, which is one of the reasons why we want to and desire the idea of a random sample from the population. Of course, this means that the characteristics, statistical values we know about the sample can be generalized more easily to the population with some level of certainty. If you, for some reason, do not have a random sample, then you have to go back, and we've discussed this before, you have to consider all of the arguments of why this sample may represent the population. But in statistical analysis, more especially in inferential statistics, the strongest claim we usually can make, the strongest mathematical claim we can make, is when we have a random sample of data. Whenever we draw inference, it's a matter or degree of certainty. We always deal with uncertainty. That is, when we have a sample, it's not a true value of the population, it's an estimate. It's a really, sometimes if a random sample, it might be a really great estimate, but it's still just an estimate. So there's some degrees of uncertainty. So we always have to remember, from a statistic or of a sample to a parameter of a population is an estimate. The general purpose of inferential statistics is to make inferences, generalizations about a population based on findings from a sample. We're going to make inference, we're going to generalize, we're going to make claims, we're going to make statements about a general population based on the best information that we have, which is from the sample that we've collected. So given the sample data, what are tenable estimates of the parameter? And we're going to do this in two ways. We're going to talk about point estimates, and we're going to talk about interval estimates. Our point estimates are going to be things that we're going to use to estimate the parameter with a single value, and our interval estimates are going to be things like our confidence intervals, which are not just one single value, but a range of values. When we consider analyzing inferential statistics, there are two very broad categories that we're going to use to help us draw inference. There's hypothesis testing, a very classical way of conducting research, as well as estimating parameters and building confidence intervals. Both are used all of the time in our quantitative research methodology. These aren't the specific procedures or analysis like conducting a t-test or conducting an analysis of variance, which we'll just learn about shortly. These are the general class of procedures. In many ways, the two are really doing the same thing from a very different perspective, from a very different theoretical perspective. And we'll see a little bit more of that as we dig into some of the ideas of our sampling distributions and hypothesis testing. But I also give this as our pause moment. Often it's helpful for us to have our own research questions out, our own hypotheses that we've been developing in our research that we might be using for our final presentation. So getting those out now may help you put context as we go through issues around testing hypothesis, estimating parameters, and as we get into our statistical analyses. Hypothesis testing is a statement about one or more parameters. For simplicity, let's just think about mu. This is the mean. This is the mean of a population. That is a parameter. We want to make a statement about what we believe about a population average. We're going to do some testing. So we test something about our sample. So we make a hypothesis, and then we're going to determine whether or not our hypothesis, the claim we want to make about the population, is consistent with the data that we have at hand, our sample data. If it is consistent, we can retain that hypothesis. If it is not consistent, we reject that hypothesis. Let's just take a pause moment so you can make sure you have your research question at the ready. Here's mine. Our research hypothesis is that those that are given healthy snacks will increase performance on a math assessment. We're specifically targeting middle school children. So we're going to have those that eat the healthy snack and those that don't, and we're going to compare the two. So in the population, this isn't just in my sample. I believe in the population of all students, right? Let's just talk really broad. Of all students that eat healthy snacks, they're going to perform better on math assessments than those that eat unhealthy snacks. More specifically, because I'm narrowing down my research hypothesis, I'm targeting 7th grade students. So instead of collecting up all of the population data, which is probably not possible on all middle school students in the country, I have a smaller targeted group, which we're calling our sample. Ideally, it's a random selection process. So my hypothesis is that the population, so my hypothesis really is about the population, not about the sample. It's that the population average score on math assessments, when I compare it from the population score for those that eat healthy snacks and I compare it toward those that eat unhealthy snacks, is that there will be an increase in performance. There will be a higher performance. There will be a higher mean, a mu, in the population. Well, I don't have population data. So I get a random sample of both groups. I've randomly selected, randomly assigned. I have now those that ate healthy snacks as a sample and those that ate healthy snacks, unhealthy snacks. and I give them their math assessment, well, I get sample means. I don't have population means, but I can test my hypothesis using my sample means. Of course, there's fluctuation in our data. There's the possibility of errors we'll talk about in a moment. But we expect we can draw one of two possible conclusions. Either the means are very close to each other, that they're similar. That means in my data, in the sample that I collect, the average of those that ate my healthy snack apples and those that didn't on their math achievement tests were the same. Or, so if that's the case, then my hypothesis was not supported. And I say, well, I have to reject my hypothesis. However, if there's a big difference, and we're just going to say, use big difference here in general, and we'll talk more about significance testing in a moment. But if there's a large difference between those two groups, then we say that my hypothesis is consistent with the outcome of my data. So I can make a claim to retain my hypothesis. So the whole goal here, and by difference, we would say that there's a big difference. Those that ate healthy snacks like our apples in our sample performed much better than those that didn't eat our healthy snacks. Then we would retain our hypothesis. So we would say, by retaining the whole hypothesis, you're making a statement like, this is a plausible explanation of what happened. By rejecting the hypothesis, you're saying this is an unlikely explanation of what happened. When we consider interval estimates instead of just point estimates, we're usually talking about a confidence interval. It's an interval estimate of a parameter. That means we want to know what are the plausible estimates that the parameter could be. So it's a range of values that is likely to hold the true value of the parameter. We are constructing an interval, and it's going to be a symmetrical interval around a sample mean. So remember, the parameter is the mean of the population. Here, in order to get an estimate of it, we're going to build a range of scores symmetrically around some evidence that we might have, which would be a sample mean. So we can take the point estimate, that sample mean, and build some sort of measure of variability around it. You might just think, as a really simple simplification of our hypothesis, what if we just want to know what is the average math achievement score in middle school children? And I mean that as the parameter. What is the average in the whole population of middle school children? Well, it's going to be very difficult again to find that out. So instead, we could go find the average. We could get a random sample of middle school children, get an estimate of the mean, the sample mean, the estimate of what the population mean would be, and use that estimate as our point estimate. But instead of just taking it as a point, we can build variability around it, and we'll see how to do that as we construct these intervals. But so instead of just being one value, we would have a range of values. It's certainly plausible that we go collect a sample of data from middle school students. We collect up our math assessment scores. We get an average of 50. That's the sample mean of 50. But it's not as useful in this case if we're just considering what we think is a plausible value of the parameter estimate. Well, we don't think it's actually 50, but it sure would be nice to be able to put a range of values around that. So in this case, we're going to talk about using things like variance measures, standard deviations, and we'll be able to put a range of scores here. So now instead of just saying it's 50, we can say it's 50 plus or minus 5, which just means the true value, we believe it is very likely that the true value is somewhere between 45 and 55. Now we're going to go back and shift gears a little bit. We're going to go back over both hypothesis testing and constructing intervals and talk about more in depth a little bit about the concepts and discuss some of the procedures around them. Hypothesis testing at its center is a chain of reasoning. We're going to use random sampling, fluctuation, and ideas from probability to help us with our reasoning. Let's set the stage for our hypothesis testing. We're going to conduct a test of hypothesis, but we're going to set up two types of hypotheses. And these are going to be established prior to collecting data, or you can think about it as prior to analyzing our data. The first hypothesis is the null hypothesis. It is the hypothesis of no difference or relationship. It is a statistical hypothesis. Our second hypothesis is our alternative hypothesis. It is our test hypothesis. It is the research hypothesis. So if we put this in context of our healthy eating example, my research hypothesis is that those that eat healthy snacks will perform better on my math test than those that don't. So the alternative hypothesis is that eating healthy snacks will increase performance. The statistical hypothesis there is all the other possibilities that it will not change. There will be no difference. So the null hypothesis would state no difference between those groups. So null, no difference. My alternative is my research hypothesis that I'm putting forward. When we explore these, there are possible decisions. And we're going to talk about those decisions in relationship to the null hypothesis. We want to reject the null hypothesis. That is, we want to say the null hypothesis that there was no difference, well, that's not true. That's rejecting it. Or we want to say that you cannot reject the null hypothesis. So if the null hypothesis is no difference and we can't reject it, then there is no difference in my data. And we're going to talk a little bit deeper about that theory. In exploring the null and alternative hypothesis, we can set these up. We're typically thinking about, for now, comparison between groups. We can also think about relationships like correlations. The null hypothesis, when we think about differences between groups, is just no difference between the mean scores of the group. So I go out, collect data. The null hypothesis is supported. It's retained. We can't reject it. So there's no difference between the mean scores. Whereas the alternative hypothesis states that there's a difference between those mean scores. Again, though, we're actually only ever going to test the null. We often say things like, we have rejected the null, and amongst the possible alternative hypotheses is our research question. We can do the same thing here when we consider issues around relationships. That the null hypothesis would say that no relationship exists amongst variables. So you can think about a correlation. Does a relationship exist or not? You may have a null hypothesis stating that the relationship doesn't exist, and an alternative hypothesis saying a relationship exists between two variables that you're studying. The acceptance of the null hypothesis, just again, is the difference between the groups is too small to attribute to anything but chance. It's just chance variance amongst groups, so they're not going to be identical to retain the null or accept the null, but there's such little difference that we just don't attribute it to anything, so we retain it. Same is true if we think about relationships, that the relationship is way too small to attribute to anything but chance alone. So if we have the two groups that we test and there's a difference, the difference is very small. We just say, well, it's just due to chance alone. Whereas rejection of the null, the difference between the groups is so large that it can be attributed to something other than chance. It's our experimental treatment's what we'd like to say that it's due to. You can say the same thing about relationships. If we're thinking about correlations, that there's a large enough correlation that we can attribute it to something other than chance, that there might be a real relationship that's occurring in our data. Now that it comes to hypothesis testing, let's go through some of the steps or stages that we're going to go through. We're going to set up the null and alternative hypothesis. We're going to set up those before we collect data. If you have existing data, you're setting this up before you're conducting your analysis. You're going to establish the sampling distribution for the null. You're going to say, what does the null normally look like? Then we're going to calculate out the test statistic. We're then going to reference the sampling mean in the distribution. We're going to take the test statistic we calculated and compare it to the distribution we established. And from there, we're going to state our conclusions. Just a few notes. We're going to be doing things like finding a p-value, a significance value for our test statistics. So you've probably heard that reference before. If not, we're going to be discussing that just a little bit about significance level. And that helps us decide whether or not to reject or failed to reject the null hypothesis. When we discuss our conclusions, we will also consider the fact that we could always have made some form of error. So we'll consider the 4 possible outcomes of our hypothesis test as well. So step 1, let's get a little bit more into the null and alternative hypothesis. The null is symbolized with that H sub 0. The alternative is symbolized with that H sub A. H is for hypothesis. H sub 0, some people call it H naught. That's our null hypothesis. H sub A, H sub alternative. Sometimes you will see that slightly differently. Somebody will specify something about the alternative there, but that's the typical symbols that we see. HA, our alternative, is consistent with our research hypothesis. We actually call both of these, both the null and alternative, once we've written them out in statistical form, our statistical hypotheses. But the alternative will be consistent with what our research hypothesis is. In our regular language, what we wrote out as our research questions. H0, our null, is the logical opposite of our alternative. The null is actually tested. It is either rejected or retained. The null, mathematically, we'll see in symbols, will always contain an equality sign, an equality relationship. The alternative will never contain the equality relationship. It's useful to repeat our language, our null and alternative. It's also useful to see our symbols, H0, our null, HA, our alternative. Always refer to population parameters, not the sample values. That's why we can state them before we even collect our data. We're going to establish these, we're going to set these hypotheses up right up front in our methodology. So for every alternative, we have a corresponding null value. So for example, what that might look like, if HA, our research hypothesis, is consistent with our alternative hypothesis, HA, we would say that the mu of group 1, the mean of group 1, is not equal to the mean of group 2. So that's a simple statement. We see an inequality there. But what that's saying is that group 1 and group 2 are different from each other. That's usually what we're saying with our alternative and our research question. The corresponding null would say, no, they're not. They're equal to each other. That group 1 and group 2, the mean in the population are equal to each other. So mu1 and mu2 are equal to each other. So let's just take a example, just really simple. Put a number in here. So let's just say that I'm using I know I have my setup that I want to see that providing healthy snacks will increase performance on math tests. And let's just say, though, that I know that the average performance on my math achievement tests in the population is 29. That is through schools and everything else, I have a value of 29 on average. My alternative hypothesis, just by collecting data on those that maybe I want to go out and collect data on those that are having healthy snacks, I would say that the mean that I would collect would be different than the average in the population value. That would be different than the existing value on average of math achievement scores. So my alternative would say that the mean of these folks, the mean in the population of people that eat healthy snacks, is going to be higher than the average that don't eat healthy snacks, or just higher than the average. Whereas the null is going to say, no, they're equal to each other. The null hypothesis says the mean of the population as the population value, the parameter in the population, the mean of all of those that I collect for group 1, our healthy eating group, is going to be the same as those that don't eat healthy. So alternative here in symbols is saying there's a difference with that inequality, and the null is saying that they're equal. Our null and alternative, our pair of statistical hypotheses, are always involve the same parameters and contain relationships that are mutually exclusive and exhaustive. That means they are in completely separate bins, but they, mutually exclusive, but exhaustive. They cover all range of possibilities. So we can have several different types of null and alternative hypothesis structures. So when we say mutually exclusive and exhaustive here, Our null hypothesis, if it has the equality sign that says the two groups that we're interested in are equal, then the alternative has an inequality. It just simply says they're not equal. It doesn't say whether they're above or below each other or a directionality. We can also have directional one-tailed tests. We could say that we have a null hypothesis that says less than or equal to. Then our alternative will always say greater than. So if we say from an alternative perspective that our healthy eating group is greater than non-healthy eating group, that's our alternative, the null must be all other possibilities and they can't overlap. And then equally we can have the null being greater than or equal to and the alternative being less than. So these are the general structures of our statistical hypotheses. Another way of stating this is that we have directional or non-directional tests. If the alternative hypothesis contains that inequality sign, it is a non-directional hypothesis, and we call that hypothesis test as a two-tailed test. If the alternative hypothesis contains a greater than or less than sign, it is a directional hypothesis, and we call that hypothesis a one-tailed test. Let's just use our example and go through two hypotheses, and we'll keep things pretty simple. So we have our hypothesis, and it boils down to our research hypothesis is that if the average math assessment of students eating healthy snacks is different than 29. I'm using 29 as a value that might be known as a population parameter, as a population mean. So if we know that, for example, just for the purposes of an example, that in the average across our district of students in 7th grade, that the average score on this math assessment is 29, we might just say that eating healthy snacks will yield a different value than 29. This is what we would call a two-tailed hypothesis. So our two-tailed hypothesis, the alternative HA, the second of those two, says that the mean that we're going to collect that would represent those that are healthy snack eaters will be different than 29. And the null says that there's just no difference. Now, really, we're interested in a more directional hypothesis, which we would call a one-tailed hypothesis. We're just going to search in one end of our distribution. We'll take a look what that actually looks like in a moment. But we might say that average assessment of students eating healthy snacks is greater than 29. This is what a one-tailed hypothesis test for the null and alternative would look like. The null would say that, no, the score that you provide will be less than or equal to 29, and the alternative says it's going to be greater than 29. Remember, I'm just putting some values in here just for the sake of an example. So that's just so that we can suppose that if we knew things about the population, like students tend to score 29, then it helps us craft our alternative and null hypotheses. It also helps us decide, are we searching in either direction when we make our claim, or are we just searching toward one direction? And really, in this case, we probably would just be looking at a one-directional hypothesis because our belief is really that healthy eating will increase those scores, not potentially decrease them. So we've stated the null and alternative hypothesis. Our next step is establishing the sampling distribution for the null. To test the hypothesis, we need to establish the sampling distribution, and in doing so, we're going to use the idea of central limit theorem. We're just going to really just touch on this. It's just the central limit theorem basically states as the sample size increases, the sampling distribution of the mean will approach a normal distribution. That means our sampling distribution is one of the standard normal distributions. So it will have a mean. It will be defined as having a mean of the population mean and a variance of the variance just divided by n, the size of the sample. We can conceptually think of a sampling distribution as containing all of the possible values of a statistic for a given sample size. When I say statistic, we're going to focus in on the mean here. So you can think of the sampling distribution as being all possible means that could have occurred for that sample size. Let's take a look at this in a little bit more, to get a little bit more conceptual understanding of what we mean here. As we think about and try to conceptualize sampling distributions, we're first going to look back to the idea of the sampling distribution, the standard z-score. So this is our normal distribution. This is the standard normal distribution for a z-score where the mean is 0 and the standard deviation is 1. We talked a little bit last time in descriptive statistics how we could either transform this, or this could look a little different in the sense that we could have a different mean and a different standard deviation. So we could take on any mean and any standard deviation we want and still be in the family of standard normal distributions. Let's just take this distribution. It's a normal distribution. We'll just say it is our population. It has some mean, mu, remember that's the mean of the values of our population, and some standard deviation. So this is our population data. I can go into that population and conduct a sample. I grab a sample. Let's just say, just for illustrative purposes, it's a sample of size 9. I collect out 9 people. I go in there and I can take those 9 persons in my little sample over there and calculate out a mean, that X bar. I can do that again and again and again and over. So I could, in theory, do this an infinite number of times. So I'm going into my population, pulling out a sample over and over of the same size. So in this case, they would be, just for illustrative purposes, again, it's just sample size 9. If you had a sample of size 20 or size 50, you could do that over and over and over again as well. Now, we have all of these samples. In theory, again, it's an infinite set of samples, to which I calculated out a statistic. That statistic is X bar. It is a mean. We can take all of those means, all of those average values, and put them into a new distribution. And we call that distribution the sampling distribution of the mean. So instead of being the sampling distribution of the original population, this is the sampling distribution of the mean for a specific sample size. In this case, if for our illustrative purposes, we said it was a sample size of 9. So we put all of those X bars into a distribution, and now that sampling distribution has certain properties. It has a mean, which should be equal to the original population value that we looked at. And it has a standard deviation of the original population divided by the square root of n. We saw that before as the variance divided by n. Here I just took the square root of that. These are just some of the properties of that distribution. Now, why do we use this is really the question. So we've gone through, we've collected out our all of our infinite all possible statistics, and now we have a sampling distribution of that statistic, which is the mean. So the sampling distribution of the mean. Now, technically, that we have a standard deviation of the sampling distribution, we call it the standard error of the mean, and that is the standard error of it is equal to the standard deviation divided by the square root of n. And we can use that. We can use that by being the sampling distribution that we're interested in establishing. And when we pull out one value of that mean, we can try to establish where it comes from in that distribution. And when it's a rare value, we might want to say something about it. When it's a value that doesn't occur frequently, maybe not rare, but a value that's infrequent, we're going to say certain things about that, as opposed to it being a value that might typically occur. Let's just also envision this as probability theory and areas under the curve. Now we think we take that one mean from the distribution so that we go through, we get a real sample of size 9. We calculate out a mean. We want to know what's the probability associated with getting that mean from that area under the curve, assuming the null population, the null hypothesis was true. So we're looking at areas under the curve. And when I have areas under the curve, it's that little triangle shape right there. That's where we pulled it from. Now we're interested in using that to draw inference from the sample, that X bar, back to the population. If it's extreme value, then it's in the tails. If it's a typical value, then it's under the central part of the distribution. Let's just keep an example simple and current. We had said earlier that the mean of the population value we were interested in, the mean for our math achievement scores was 29. So we retain that here. We go through, we have a mean of 29. And let's just say that the standard deviation, just for illustrative purposes, so we can go through and develop a example, that the average, the standard deviation around that score is 6. In order to calculate out the standard error, we can just plug in that value of 6 and divide by the square root of n. In this case, our running example, we were just saying that our n, the sample size we collect, we got 9 students to take a test in our example. So we would take 6 divided by the square root of 9. Square root of 9 is 3, so 6 divided by 3 equals 2. So the mean of our sampling distribution that we're interested in is 29. And the standard error of that mean, or you can think about it if it's easier, as the standard deviation of the sampling distribution, and that value would be 2. This helps set up our problem. It sets the stage. We've established a distribution. We've gone through, we've stated our null hypothesis. We've established our distribution for the sampling distribution for the null hypothesis. And now we need to actually compute a statistic. So our next step is we're going to compute the statistic. Here, the statistic is a mean, and it's a mean for a sample. So in our example, we have collected up a data set with 9 participants. We compute the mean from a random sample, and we calculate it out to be 34. If you want to go back, our last descriptive statistic lecture goes into computations of the mean. So after I've done that computation, I now have calculated a value of 34 that I can use for comparison purposes. So now we want to be able to reference or position where the sampling mean that we calculate is compared to this in the sampling distribution. I want to think about it as how many standard errors away is the hypothesized mean, the mean we thought about before we even had data, compared to the sample statistic, the statistic we actually computed. We can determine the probability of obtaining that sample mean that is indeed different from that expected value. So let's just go ahead and walk through our example numerically, and then we'll actually place it in that distribution. So our example was, we believed that ahead of time, we have that as our null hypothesis that the mean of the population was 29. We computed in our sample statistic a sample statistic of 34. So that would be the sample statistic for our 9 participants that were, in this case, in our healthy eating group. Then we also computed out a standard error of 2. We just took the population value of standard deviation, which was 6, and divided by the square root of 9. So it was 6 divided by 3, which equaled 2. We already did that. So we have those 3 values. We're going to place those 3 values into our equation, a very simple equation. Our numerator is just the difference between the 2 scores, and the denominator is just the standard error. So what do I mean by the difference of the 2 scores? Well, we take 34, our sample mean, that X bar, subtract mu, our population value, and we get 5. So the numerator, relatively easy, right? We're just taking 2 numbers and subtracting them. And then we just need to divide by 2. So we take our standard error in that denominator, and we divide by 2, and we ended up with 2.5. That's another way of saying we are 2.5 standard error units away from the hypothesized mean. Our sample mean is 2.5 units away in standard error units from the hypothesized mean. So that's the distance between our sample mean and hypothesized mean. I'll try and explain this a few different times. We're we can look at our sampling distribution as standard error units. So on that axis there, on the x-axis, we can think about that distribution as being our sampling distribution of the mean. If you were 0 units away, you would be in this general area. I mean, specifically, you'd be right under the 0 here, the center of our sampling distribution. So 0 units away would indicate that we are at that same value, and we would just say, well, there's no difference. But also, one should think about our standard error units. Most of the time, if we were to sample and get a mean, it's going to be in the central region. If you look at those percents there, you see about 70%. I'm just rounding. About 70% of the time, we're going to find a mean that's within a little bit more than one standard error unit away, plus or minus. There are rare circumstances, though. Like there are still occurrences, but the area under the curve, when you get out really far, plus or minus 3 standard errors away from the middle, we see it only happens like 0.13% of the time. And even 2 standard errors away, we see that only the area under the curve, one for each curve, is about 2.14. So a little over 2% of the time, the area under the curve, we find values that are about 2 standard errors away from each other. So if we have a value of 29 at the middle instead of a 0, and we calculate out a value of 34, it's about 2.5 units in that general area there. It's relatively far away from each other, and it doesn't happen that often. We can sort of set the stage here using this conceptually in our hypothesis testing. Before we go on and examine this in a few other ways, I want to mention that these are z-scores. So what I'm actually calculating, 34 minus 29 divided by the standard error of 2 equals 2.5. That 2.5 is a z-score. The sampling distribution we're looking at is 4 z-scores. Instead of having to redraw the distribution every time with a different mean and a different standard deviation, we just do these calculations, we come up with these z-scores, and we just put them on the same distribution. You can see where I've slid over the 2.5, and I've placed it in between the 2 and 3 standard error units there. So those scores, 0, 1, 2, 3, 4 on that x-axis, those are our z-score units. So we calculated out something in that region beyond that second z-score. Because of these nice properties of our sampling distributions of the mean, we can establish some really easy search criteria. For a one-tailed test, we just search in one of the 2 tails. We search in the upper tail or lower tail. Those are the fringes of our distribution. For a 2-tailed test, it's non-directional, so we can search in both tails. Typically, we set our search criteria to something like, let's just say, 5%. We call that 0.05. So if it's a one-tailed test, we're looking for 5% on area under the curve in one of the 2 tails. If it's a 2-tailed test, we just split it in half, and we can look at 2.5% of the area in either curve. So let's take this and use this in our example to make it a little more concrete. Let's just come back to our equation from our running example. We hypothesized ahead of time that the null hypothesis stated, and we'll just keep a simple no difference hypothesis for now, 2-tailed difference, and then we'll see a 1-tailed directional hypothesis. So our null hypothesis simply states that the hypothesized value of our population, which was 29, should be equal to the sample that we collect. Our alternative just says it's difference. We went through, we calculated at our value, 34 minus 29 equals 5, and then we divided that by our standard error of the mean, which is the same thing as it's the standard deviation of the sampling distribution of the mean. So we just calculated that. We got a value of 2.5. Let's see what that looks like. Let's give some graphical context to this. So here's our distribution. This is the distribution of our sampling distribution of the mean. We hypothesized ahead of time that the mean, the average score of this distribution, is 29. The standard error of that mean is equal to 2. It was equal to 2 because we calculated it out. We knew the standard deviation of the population was 6. We collected a sample size of 9. We took the square root of that and we calculated that out to be 2. So we know the properties of this distribution. It has a mean of 29 and a standard error of this mean, the sampling distribution of the mean equals 2. We calculate a score. We go in, we get that sample value, and we calculate that score up to be 34. It's in that general area of the distribution, relatively far away. We can compute, and ahead of time, we can just place search criteria. And in this case, because we're going to look in both tails, we can say our search criteria is 5%. So we're going to look for values that are in either area of the tail of the distribution, because we're looking at a two-tailed test. We just split that 5% in half. So we look in the lower end of the distribution for 2.5% and the upper end for the area under the curve of 2.5%. And we're looking to see if our sample mean falls in that area. Now, if this were a one-tailed test, and our hypothesis likely would have drawn us maybe toward a one-tailed test, we would search the area of just the upper tail here because we didn't really care about the lower end of the distribution. That is, our hypothesis would have stated, our alternative hypothesis would have stated that the sample mean that we would collect based on healthy eating would be greater than the hypothesized mean. So that means that our sample X bar of 34 will be greater than 29, and indeed it is, but it's not just greater than it. It's greater than it in enough of a distance from it that we could say, start to begin to use the language of significance and rejecting the null hypothesis. And that's getting into our final stage of our hypothesis testing. Now that we looked at what our sample mean and our population mean look like, relatively speaking, on the sampling distribution of the mean, to give us some sense of what we're doing here with this equation, we can come back to it. So in this equation, we just took a value of our mean, 34 for the sample and 29 from the population, and subtracted them. We divided by the standard errors, and we got a value of 2.5. Well, what this does is this gives us that point on the distribution we just sort of looked at for our value of X bar for the mean, but also we can look at it as having a value of that we calculated corresponding to a value of 2.5. That is, in terms of the standard error units, we are 2.5 standard errors away from the hypothesized mean. The sample mean is 2.5 units away from our hypothesized mean. We could use our distribution theory to get a probability, a chance that that would occur. That's what we were doing when we were looking at those probability distributions, but we were doing it in a more intuitive way. In your textbook, if you were to take that value of 2.5 and look it up on your table A in Appendix 3, you would see that you would end up with effectively about a 0.0062 probability of acquiring that value of 34. That is, the difference between 34 and 29 divided by 2 was 2.5. So we have a very, very small probability of finding that value if our hypothesized mean were indeed true. So what we are actually doing in significance testing is we're going to take those values, in this case, a very small probability, and compare it to an established level of significance. So let's take a little bit deeper dive into significance testing. In our final stage of hypothesis testing, we're going to state our conclusion and we're going to have a rationale for it. We often use tests of significance to do that. So we have a statistical analysis which helps us decide whether to accept or reject the null hypothesis. you'll hear things like alpha level, level of significance, p-values. These are all established probabilities ahead of time, which serve as a criterion to determine whether or not to accept or reject the null hypothesis. Most frequently, you in education and psychology and social sciences, you hear values of like 0.01 or 0.05. Those are significance levels. A significance level is a probability used to test our hypothesis. Those commonly used values, if we exceed those probability levels, that is, if we go out in our tail of our distribution and we're testing our hypothesis at a 0.05 level, a 5% area that we're searching for, and it exceeds that value, then we say our statistic is significant. If it doesn't exceed that value, then we say that we accept or retain the null. If we exceed that value, we reject the null. Let's pull together our testing and our statistical analysis that we're actually conducting right now. So we went through, we computed the difference between our means, divided it by the standard error, and we came up with a value of 2.5. This value is a value you would compute from a z-test. We are in standard error units away. If you remember z-units from z-scores from our last descriptive statistics lecture, well, now we're to have a z-test. That is, we can standardize these values. Instead of talking about it as units of 34 and 29, we could talk about it as units of where our mean is 0 and our standard deviation is 1. But for now, we can just label this. We conducted this little test and we got a value of 2.5. That value of 2.5 is associated with a probability under that normal distribution, under that normal curve. That probability associated with 2.5 is 0.0062. That is, we have less than 0.6% of the time that we would find a value as extreme as 34. Or in standardized units terms, we would call it a value of 2.5. If this were a two-tailed test, we would simply have to multiply that value by 2, as we might also find extreme scores in the other direction. So you could imagine you find a test value of 24. 24 minus 29 would be a value of negative 5. And negative 5 divided by 2 would be a negative 2.5. So you could find a negative value just equally as far from the mean, the hypothesized mean of the population. So we would just multiply those by 2, 0.0062, and we come up with a value of 0.0124, or just think about it as approximately 1%. It's about a 1% chance to find a value as extreme or positive or negative as that value of 34, if you were to look in both areas of the curve. And that's what we were doing before when we were looking at our distribution, the sampling distribution of the mean, and we were placing our values on it. Let's just do an overall review of our hypothesis testing. We're going to set up the null and alternative hypothesis. Here I'm just establishing it as a two-tailed test. We could look for extreme scores in either tail. And we're going to set or establish a level of significance ahead of time. And we'll call that 0.05. So that level of significance, again, that is our critical probability value. That probability value is established by us, the researchers, and 0.05 is one of the most common values that we use. Then we establish that, we establish our sampling distribution. We know that we're doing this for the mean. The test that we use, that simple difference between the two means divided by the standard deviation, we called it the z-test. But we're going to use the idea that we're going to use the sampling distribution of the mean, and that's going to help us establish what sampling distribution we should look at. And for us, it's just going to be a standard normal distribution, which is pretty fortunate. It's a very common distribution to look at. Next, we calculate out the statistic. Our test statistic for our sample was 34. We compared 34 to 29. Difference was 5. We divided by our standard error of 2, and we got a value of 2.5. 2.5, if we're looking at a two-tailed test, our scores were associated with a probability of, in each tail was 0.0062, so we multiplied by 2. So overall, if we're looking in either tail, the total probability associated with that. This would be the calculated probability, is basically about 0.012. So a little bit more than 1% of the time we would find these values are more extreme. We can then compare that 0.0124 to our established ahead of time alpha level, our probability. So that was a value of 0.05. And we can say the probability that we found of 0.012 was less than the probability of 0.05. So if in this example, because in this example, we chose the level of 0.05 significance ahead of time, we could say we reject the null hypothesis because we calculated out that value of 0.0124, and it is indeed less than the level of significance we were originally searching for, which was 0.05. Now, if it were the other way around, that is, the value that we calculated were above 0.05, we would say that we failed to reject the null hypothesis. So you may be asking questions like, well, where do I get these probabilities for my z-scores? So we went out, we calculated out a value, and you calculated out the 34 minus 29 divided by 2. We got a value of 2.5. Well, where you get those values is you can look them up in tables. Also, if we're doing computations, when we get to our other analytical techniques, in the software package, it will give us the probability that's associated with the value that we're calculating. We're not going to get that far into it in this class. I'm just kind of giving you the very, very quick glimpse at it. We look up those values in tables. There's t-tables. There's tables for analysis of variance. We call those F tables. There's tables for z-scores. We're not really focusing on that in this class, but I do want to show you some of the more common values here, and I'll repeat them again in our confidence intervals. One thing to note here, if we look at our z-scores, we see those values at the very bottom I just highlighted of 164, 165. You see they're almost in the area beyond the z. If you look at that column, they're almost 0.05. So 1.645 is the number we kind of interpolate that to be 0.05. And that's if you're looking this up in a table. That's kind of how you would look this up for the area beyond the z. So that beyond the z is into the tail. So let's just take a look at the common values now. For our z-scores, here are some of the most common critical values that we use, and they're associated with the area beyond the z, which is just associated with our p-values. So if we wanted to look in those two tails of our distribution, for 5% chance for a level of significance of 0.05, we can see that a value of plus or minus 1.96 will get us that value of about 2.5% in each tail. So that's how we determine some of these. And if we're looking for 1%, those z values of 2.576 give us a collective of 1%. There's a 0.5% that we get to search for in each one of those tails. If we're just looking for a one-tailed test at 5%, we'd look at a z-score of positive 1.645 for the positive end, or negative 1.645 for the negative end of the distribution. This is just to give you some more intuitions. I'll go over this again a little in our confidence interval when we discuss confidence intervals. Let's remind ourselves of a few things when we're conducting hypothesis testing. So we've gone through, we've built our null and alternative hypothesis, and now we're going to make a decision. The decision is always about the null hypothesis. That is, the hypothesis of no difference or relationship. So when we make these decisions, we can either reject the null hypothesis or retain the null hypothesis. That means not reject. Maybe some people would say accept the null hypothesis. So we either reject the null or retain the null. Those are the decisions that a researcher makes. But there's actually 4 possible outcomes from those research decisions. For either decision, there is the possibility that an error has been made because the true value of the parameters will not be known, because the entire population is not measured. Tests of a specific hypothesis will yield one of these four possible results based on the actual situation in the population and the decisions of the researcher. Let's take a look at our table in a little bit more detail. Going across the top, truth and false are about the null hypothesis. So truth means indeed the null hypothesis should not be rejected. It should be accepted. It should be retained. False means we should have rejected it. Going along the side, our rows, these are the researchers' decisions. They did not reject it, or they accepted it, or they rejected it. So it's not reject versus reject, the null hypothesis. So if a true hypothesis is not rejected, or a false hypothesis is rejected, there's no error. So that means the decision we made about our sample was also reflects the truth of the population that we cannot measure. If a true hypothesis, however, is rejected, a true null hypothesis is rejected, or a false null hypothesis is accepted or not rejected, we say, we have made an error. And there are two types of error. There's type 1 error, which we reject a true hypothesis. We call this an error of alpha, an alpha error. And there's type 2 errors. We accept a false hypothesis. That's a beta error. Only one type of error is possible in any given statistical test. Generally speaking, reducing the risk of one type of error increases the risk of the other type of error. So ways we can control type 1 error using that idea of alpha, our significance level. As alpha becomes smaller, as we go from levels of like 0.05 to 0.01, even in more extreme chances like 0.001, there's less chance of a type 1 error. As a matter of fact, that is the chance of a type 1 error. So if you test at alpha equals 0.05, there is only a 5% chance of making a type 1 error. And that's part of the reason and rationale behind selecting those type of small values for alpha. Confidence intervals in hypothesis testing are really intermingled. We're going to see that a lot of what we just learned about hypothesis testing will be true when we look to build our confidence intervals. Those are the interval estimates around the parameters we're interested in measuring. We spent a lot of time going over the sampling distribution and sampling statistic and hypothesis testing. Fortunately for us, we can just use those same concepts in confidence intervals, so we don't have to go over them in the same level of detail. Confidence intervals are based on a desired confidence level. It's a defined probability that the interval will span that population. So some commonly used levels are 0.95 and 0.99. We say we have a confidence interval of 95% or 99%. That defines the probability of that interval or the percent of that interval. So for example, in a 0.95 confidence level or confidence interval that we're constructing, the 0.95 confidence level, the researcher wants an interval on the scale of measure that includes 95% of the area of the sampling distribution. Those values that we saw earlier, those Z values, those values associated with critical values for our confidence intervals. For a 0.95 or a 95% confidence interval, we associate a critical value or a Z value of 1.96. And the values associated with a 99% confidence interval or a 0.99 confidence level is that value of 2.576. It's useful to start off, let's build a confidence interval and look at the computational formula. But first, let's remind ourselves that we are constructing the symmetrical interval around the mean. So we have a mean and we're going to get some interval around it. The mean is our statistic. It's going to be our value from our sample. So we're going to take that statistic, the mean in this case, and we're going to add and subtract the critical value times the standard deviation of the statistic. I will remind you that that value, the standard deviation of the statistic, is the standard error of the mean. So we can just call it the standard error. So we're going to take, and that's the standard deviation of that sampling distribution of the mean. So this is what the equation looks like. But really, it's two equations. You're going to take the mean and add the critical value times the standard error, and take the mean and subtract the critical value times the standard error. It's much easier to see in an example. So we'll go ahead and do that. For example, let's work with one of the most common types of confidence intervals, a 95% confidence interval. This will include 95% of the sampling distribution that we're interested in. We're going to use a critical value, a z-score value of 1.96. We saw earlier that 1.96 meant there was still 2.5% in each area of the tail. So this means that because there's 2.5% in each area of the tail, the remaining middle part of the confidence interval is 95% of the sampling distribution. Now we know how to set it up. We're going to follow our equation. We have a z critical value, which is 1.96. We've already done the calculations, right? We already before calculated out for our sample mean, we got a value of 34. We computed a standard error. That was that value when we said the population value was 6. We divided by the square root of 9. We ended up with a value of 2. So our standard error of the mean of the sampling distribution was 2. So we have those 3 values. That's all we need to plug into our equation. So we now have 34, the mean, and there's going to be plus some value on the interval and minus some value on the interval. So it's 1.96 times 2. If you're having a problem with hearing the decimal places, just round to yourself when you see these. So it's 34 plus or minus 2 times 2. That's approximately what it is. So let's go ahead and do those calculations. So 34 plus 1.96 times 2 is equal to 37.92. And 34 minus 1.96, the critical value, times 2, our standard error, equals 30.08. So we can approximately think about this as 34 plus 2 times 2, the critical value times the standard error. The standard error just happens to be 2 this time. It could be another value if we had a different sample. So we can see that just approximately, our interview goes from 20 to almost 30, to almost 38. So what we would say about that interval now that we've done calculated, we have an interval of 30.08 to 37.92. We would say we are 95% confident that this interval contains the population mean. Let's just try the same thing, but instead of a 95% confidence interval, let's do the 99% confidence interval, because those are also the two that you'll most likely ever calculate. So we have a critical value. Instead of 1.96, our critical value is a little bit larger. It's 2.575. But our mean and standard error are still the same. So the only thing we really have to change is going to be the critical value. So we'll go ahead and plug that in. So it's now 34 plus or minus 2.575 times 2. So 34 plus 2.575 times 2 equals 39.15. And 34 minus 2.575 times 2 equals 28.848. We can sort of just give a rough estimate here, just for those that, decimal place, hearing those decimal places isn't helpful maybe for you, but you can think about it as rounding that 2.5 just to help us understand. It's 34 plus 2.5 times 2, which is 2.5 times 2 is 5. So 34 plus 5 is approximately 39 here. And 34 minus 5 is approximately 29. That gives us our range for our confidence interval, right? So our range was 28.84 to 39.15. And here we would just say we are 99% confident that this interval contains the population mean. I'm just going to do this one more time for the conceptual visualization of what we're doing. So we have the 95% confidence interval. We're going to have our critical value is set at 1.96. Same equation. It's our statistic, in this case the mean, plus or minus the critical value times the standard error. All right, we already set this up. In this case, for the 95% confidence interval, this is our equation, our set of equations, 34 plus or minus 1.96 times 2. So we go ahead and do the negative side, and we calculate out a value of 30.08. And we do the positive side, and we calculate out a value of 37.92. So we might just visualize it as this band, right? We know the middle point in this case was 34, and we went down approximately 4 units to 30 and up approximately 4 units to 30, approximately 38. So that's our band. That's what we might visualize it. But more importantly, we can see that the idea of this interpretation, that it's the 95%, we're capturing 95% of the sampling distribution, the centermost part of the sampling distribution. We could overlap our sampling distribution, right? So our confidence interval, our 95% confidence interval, is at that center part of our distribution, right? So that center part of the distribution ranges from a z-score, that critical value of 1.96, negative 1.96, to positive 1.96. If we were doing this for a 99% confidence interval, we're just going further out into the tail so that we capture 99% of our sampling distribution of the mean. For those that are interested in thinking about this a little bit more, it's okay if you don't want to, but for those that are, remember the population parameter. We said we kind of knew it in this one. We knew that normally 29 was the score for those taking our math test, and that we took this sample, we created a sample of 9 persons, 9 students, and I got a score of 34 on average after we fed them healthy snacks. So we could kind of put these two together, the idea of hypothesis testing and confidence intervals. We see that in the 95% confidence interval, that 29 would fall out of that boundary of 30 to 28. That's the same thing that you're doing with your null hypothesis testing. You're really looking at 2 overlapping distributions and seeing whether the middle falls within each other. We're not going to get into that in detail in this class. That's usually what I do in my Intro to Stats class. But just for those that are interested, notice that the 95% confidence interval does not actually contain the parameter in the population. The 99% confidence interval does. The 95% confidence interval here between 30 and 38 does not contain 29, whereas when we broadened it out, we did contain 29. So the interesting thing here is, first, the size of your confidence interval, the percent of the sampling distribution that you're trying to capture, it matters. And the other thing is we can look at overlapping confidence intervals if we knew the true parameter. If we knew a value that we were comparing it to, even if it was another statistic we were comparing it to, we could kind of use confidence intervals as the same way we use our hypothesis testing. The two are directly related, but we just focus here first on the statistic, whereas in our hypothesis testing, we're focused on the null hypothesis and either rejecting or accepting the null hypothesis. Now we're going to get more involved in our methods of analysis. We're only going to be hitting the highlights of these. We're not going to get into any deep computations. The t-test is very similar to the z-test, so I might draw allusions back to the z-analysis, the hypothesis testing we did. But just know the methods of hypothesis testing and confidence intervals, they really impact all of the analyses that we'll talk about at a high level. What's very useful to know when we go to look at all of our other methods of analysis, no matter how complex or even how simple they all use the same chain of reasoning. Whatever the inferential statistic, whether we talk about it as a simple statistic like a t-test or get more complicated in regression analysis or analysis of variance, just discussing those things, that the chain of reasoning comes back to this same ideas around hypothesis testing and estimating parameters. So even if you haven't mastered all of the elements of advanced statistics, that's fine. Let's get the idea of this chain of reasoning down one more time. Before we go over the specific methodologies, it's just useful to remind ourselves what we're really doing in inferential statistics. We're doing the same thing we did earlier in the semester when we discussed issues several times about random selection, random assignment, drawing a random sample from the population. So if we have a population of values, in this case, we're going to go back and use the smiley face example. So we have a population of persons and we want to know things about the persons. The things we want to know are usually around our dependent variables. I've used math achievement as a variable, a dependent variable for my hypotheses. You may want to think about your hypotheses, your dependent variables you're interested in. We have a population. We're interested in some dependent measure. We're interested in some attributes of that population. Again, you might think math achievement, reading achievement scores. You might think a wellness scale, a happiness scale. You may even be thinking about height and weight values of a population. The population has some values. So some parameters that we might be interested in investigating. So for example, our population has a mean score for the math achievement test that I'm interested in. So if I were to take this population, I would say this were all middle school students, and I had a math achievement test for them. There's some actual average value. There's some mean value for those students in the population. Whenever we're using a sample, a random sample to represent the population, we need to think about the chain of reasoning. Eventually, we want to draw inference from the statistic back toward the sample, but first, we use random sampling when we are collecting our data, when we are acquiring a sample, so that we can reason first from the population. We draw a random sample. That random sample represents the population. So in that sample now, we can do some statistical analysis. That is, we have selected a random sample and we can compute a measure of the sample. In this case, I'm just computing a mean for simplicity. So now we have conducted our analysis from the sample, and this sample is representational of the population. So we have our statistic we're interested in. In this case, I'm just using the mean as our example. But we know that random sampling also produces random sampling fluctuations. So we can use, as we did before in hypothesis testing, the idea of our sampling distribution. So we compare the statistic to the sampling distribution, and we say whether it's a typical or atypical value. And we make statements about rejecting or retaining the null. Well, those statements are theoretical statements. So we're going to take the idea of our mean and the distribution that we compared it to. We made a statement about it. Our statement was reject or retain it. And now we can relate that back through. We can take that chain of reasoning. We can say something like, we rejected the null distribution. We rejected the hypothesis of the null. And in doing so, we're going to say that the alternative might be one of the acceptable explanations. We're not saying the alternative is true. We're not ever saying the alternative is truth. We're just saying because we rejected the null, we might consider the alternative as a plausible explanation. No matter which of the methodologies we're using, we've gone through, we've calculated out a statistic, we've come up with our decision of rejecting or retaining a null hypothesis. So we're using that idea of rejecting or retaining the null hypothesis is us using that theory based on distribution theory and our probabilities that we're making a correct or incorrect decision. And we use that as our statement of inference from a sample statistic back to the population. Typically we never know the actual population values for our parameters. So we're saying we calculated out our statistic or our analysis in the sample, and because of these findings represent what the population should look like. As a reminder, we're never certain. We don't know truth. That is, it's so rare that we ever actually know a population parameter or actual population values, that we're talking about degrees of certainty or confidence. So we're using probability theory in our hypothesis testing, and we're doing things like testing a hypothesis at a 0.05 level. That means that there's a 5% chance that we're making an error. So when we go through and we conduct this reasoning, we set up our hypothesis, our null hypothesis, and say, well, if we reject it, we rejected it, but we still say there was a 5% chance we made a mistake. That's what we're doing with significance testing. So we're using probability theory to say how confident we are in our results, and that confidence translates from our sample back through to our population, and that's the statement. The claim we're making is not a claim of proof. It's not a claim of truth. It's a claim of confidence. To what degree are we confident that the sample statistic and our findings represent what we saw in what we would see in the population? There are many analyses, many distributions that can be used. You'll hear us talk a little bit about chi-square. There's the f-test, there's the t-test. All of these actually represent different distributions than the normal distribution. However, one of the critical things, and for our understanding, if we understand how hypothesis testing and confidence intervals work with the normal distribution, it works the same way with other distributions. So we're not going to get in this class into the details of other types of distributions. I might mention some simple characteristics, but we're not going to examine deeply like the F distribution for analysis of variance or a chi-square distribution. However, we don't need to, because if we understand this chain of reasoning, then we understand what we're doing in all of hypothesis testing, whether it's toward a normal distribution and a z-test or toward a F distribution and analysis of variance. It doesn't matter. It is by far more important that you understand the idea of reasoning and the chain of reasoning, because our statistics are going to be done on the computer. If you get more interested in conducting analysis, you're going to be using statistical packages like R, SAS, SPSS, Python, whatever it is you might use, Excel. You're going to be using those statistical packages. So understanding the chain of reasoning and understanding what it means when we say our statistic is significant based on our level of significance we set based on probability theory. And from that, we reason backwards that we can say that our statistic represents our outcome represents our population. There are many types of techniques. We're going to go over a few classes of procedures like the t-test and ANOVA and regression, but there are many other forms of techniques that we use in statistics. We're going to talk about two general categories that your book talks about. There's parametric analysis, there's parametric statistics we use, which make assumptions about the nature of the population from which we draw a sample. And there's non-parametric analysis, which make fewer assumptions about the nature of the population from which the sample is drawn. A few things to mention here. Non-parametrics automatically sounds a little bit better because we're making less assumptions. However, the parametric techniques that we tend to use are much more powerful than the non-parametric techniques. That means that we are more likely to reveal a true difference or relationship when one exists. Of course, you must meet the assumptions of the statistics. So typically assumptions are things like we assume some form of normality, some sort of independence or homogeneity of variance. Those are the types of things we assume. I might mention some of those things again, but in general you should know that we make assumptions with parametric statistics, which we don't have to make as many with non-parametric statistical analysis. However, those non-parametrical analysis often just not only are not as powerful, but sometimes fail in as sample sizes increase, and I'll mention that again later on. We can break down the methods of analysis even a little bit further. We talk about correlational methods, and those methods really are just looking for associations between variables. Then we have comparison of means, which are methods that testing we're looking for differences between pairs of means or between groups of means. In regression, These tests assess if there's a change in one variable which predicts the change in another variable. And in our non-parametric statistics, we often just use those when some of the assumptions required for a parametric statistics don't work, with the big caveat is that not every single statistic has a non-parametric equivalent. So most of the statistics we're just talking about are what we call univariate statistics. They're univariate inferential statistics. We have one dependent variable at a time that we care about. You could have multiple dependent variables, but in the statistical analysis that you're actually conducting, that you're actually computing, you only use one dependent variable at a time. There's also multivariate techniques. For all the techniques we talk about, there's a multivariate technique for it, which is just a fancy way of saying at one time we use more than one dependent variable, so two or more dependent variables. And then there's a whole bunch of other techniques we're not going to get into the details of. I'll make mention of meta-analysis toward the end, but there are latent variable techniques, there's Bayesian analysis, there's simulation designs that one can run. So this really is just touching on the ideas, and I want to provide you that there's a general framework out there for the types of analyses that we're going to do. And we're just going to touch lightly on the first several techniques, like comparing means, a little bit about regression and ANOVA, and some correlational analysis. There are some general assumptions of parametric statistics that we make. I'm going to go over a couple of those general assumptions. The first one is that in general we say that it's measured on an interval or greater scale, so an interval or ratio scale. However, sometimes we have what we call robustness to this assumption that data that's on an ordinal scale performs well enough like an interval scale that we can use it. So there's always assumptions, as an example, interval or greater scale, and there's always robustness. Each statistic is really tested to see how robust it is, so we won't go over every single example, but I'll just tell you in general what we expect is that when we measure our dependent variable, that dependent variable has been measured and will be analyzed on an interval level scale or a ratio level scale. We expect independence of scores. This just means that our observed scores are independent of each other. So one person's in group 1, that same person isn't in group 2. There's an exception of this when we talk about dependent measures or repeated measures, but we account for this in the statistic. So for most of our parametric statistics, when there should be independence, we expect that independent assumption to be upheld. We also expect there to be a normally distributed population, but really this only is true if the sample size is lower than about 30, maybe 25. This doesn't mean that you need 30 participants in your sample. This is not sample size determination. This is a mathematical property. As sample sizes get bigger and bigger and bigger, as they hit 20, as they hit 30, as they hit 100, the normal distribution assumption goes away because of the properties of the sampling distribution of the mean. I won't get into it that much now, but just know that this assumption is true, but really just for small sample sizes. And then our final assumption I'll talk about more generally is this idea of homogeneity of variance, which is just a fancy way of saying that the dispersion or variances of our scores, we expect them to be about the same group to group. So if I have a treatment group and a control group, what I expect to see if I were to calculate a variance or standard deviation for each one of those groups individually is that they're approximately the same. They don't have to be equal, but that they're close. The first method we're going to consider is the t-test. But this really isn't different than what we've done before by any substantial margin. The t-test exists simply because we don't really know the population standard deviation. If you recall, in our hypothesis testing, we went through examples and I said, well, we know the population standard deviation. That rarely ever happens. So instead of using the population standard deviation, we substitute some version of the sample standard deviation. And that depends on whether or not we have a one sample t-test, we're just looking at one sample, or whether we're comparing two groups to each other. It depends whether those are a independent or dependent test, which I'll go over in a moment. But in general, instead of having a population standard deviation, a population value, we substitute it, and we substitute it with the sample standard deviation. This substitution gives us a distribution that looks a whole lot like the normal distribution, but it's not exactly the same. It's just very similar. as a matter of fact, if you somehow, of course you can't have this, but if you somehow had a sample that were infinitely large, it would look identical to the normal distribution. The two distributions that we would be talking about, the sampling distributions, would be the same. However, as we get really close, like as you get to values where you have relatively large samples, the normal distribution and the t-distribution that we use for the t-test look really the same. The t-distribution, you can think about it. It's just almost exactly like the normal distribution, but we define it a little bit differently. We define it with what we call degrees of freedom. So a t-distribution, because there's as many t-distributions, technically there's an infinite number of them, but there's as many t-distributions. There's one for each degree of freedom. So let's just consider this. So the t-test, we say, is a family of distributions, and it's defined by its degrees of freedom. So each t-distribution is determined by degrees of freedom. So what are degrees of freedom in more detail? They are the number of ways data can vary. So imagine we want to test a hypothesis about a population mean. If we compute a sample mean, once n-1 scores are calculated, the last value is determined. So for example, we calculate out a sample mean from 3 values and it equals 2. We know the first 2 values. Let's just go through. We calculate out a mean. We knew the value was 2. We know the first 2, identify the first 2 values are 1 and 2. What is the third value? Take a moment and think about it. That third value is not free to vary. It must equal the summation, that must equal the remainder to make that mean equal to 2. So that value must be 3. It is not free to vary. So when we think about calculating out conducting a hypothesis test on a population mean, we know that by calculating out the sample mean to represent the population mean, we have to calculate out one thing. And by calculating out that one thing, in this case, the sample mean, we have n-1 things that are free to vary. This is just meant to be an example so you can get a feel of what the family of t-distributions look like. If you look at that blue distribution, the purplish blue distribution of degrees of freedom 1, compared to the normal distribution in black. See, there's a big difference between those two, but even as we get to values of 2, 4, 10, as you get the degrees of freedom of 10, and that basically means, just imagine you have, 12, 13 people in your sample. These degrees of freedom, the information that you have 11 pieces of information, so you have 10 degrees of freedom. It almost looks like the normal distribution. So when you get up to values of like 40, 50, the t-distribution really looks like the normal distribution. Now it matters. You do have to use the t-distribution instead for technically, but for us, for conceptual purposes, the t-distribution is a family that really just looks like any other standard normal distribution. It's just slightly different. There's a little difference in the tails, and there's a little difference in the center of the distribution. I want to highlight a little bit about t-tests and the different types of t-tests that there are. First, let me reiterate. A t-test and a z-test. A z-test is basically what we were conducting when we were doing our hypothesis testing. A t-test is simply done because we do not know the population standard deviation. We instead use the sample standard deviation. There are different types of t-tests. Actually, what we were looking at before, we were comparing a sample statistic to a value of the population. In a t-test, we would call this a one-sample t-test. That is, we gather a sample and we compare it to some known population value. Now, often, even with a one-sample t-test, we don't absolutely know a population value, but we may hypothesize a population value. So, for example, if I know in general IQ scores are on average are around 100, then I may use that as my population value and might gather a sample and say, well, I think the sample that I'm gathering from my university, that the sample that I'm gathering, I'm going to test them and then give them an IQ test. And I think they're going to be above the norm, above the average of a population value of 100. So I could gather them as one sample and compare them to that population value. In a one sample t-test, though, we don't know what the true standard deviation would be. So instead, we're going to use the sample standard deviation. There's also other types of t-tests. There's t-tests, what we call for independent means. So we're comparing two groups. We're not comparing a sample to a population value. We're going to compare a sample to another sample. Well, we've been talking about these types of designs all semester. We're going to examine the difference between the mean on a score for an experimental and control group. We also have dependent means. Dependent just means there's some correlation amongst these t-tests, and usually that comparison is because we are testing people on a pre or post-test design. A lot of those pre-post-test designs we saw just mean that we test a person at time 1, then we test the same group of persons at time 1, we test that group of persons in time 2, and we're going to see if change has occurred. If we're looking at that, that's a dependent or a repeated measures means analysis that we would be conducting. These are the three most common t-tests. A one sample t-test, we just collect up data from one group compared to a population value. A two sample t-test for independent means, we're comparing our classical experimental control group. And our t-test for dependent means our repeated measures. We just have a group, a single group, like a classroom that we're testing at time 1. Some intervention occurs and we test them at time 2. So those are the three t-tests. Now we may have other designs, research designs, and there are other statistics we'll see that work with those other types of designs. This is just a really simple, basic type of analysis when we're really just comparing two groups to each other. Let's just use our same example. You can insert your example here. This is a good moment to take your research hypothesis instead of mine and use similar or same values. So I've been using my average snacking and hypothesis. I'm just going to focus on the two-tailed test. You can also have a one-tailed test here too. But in a two-tailed hypothesis, I may know through history, right? I may know that previous examples or the best information that I have on our math assessments is that students typically score around a 29. That's their average score. We're going to use that as our population value, but I don't really know what I don't really know what the standard deviation should be around it. So instead of doing our z-test calculation, we're going to substitute in, do the same analysis, but we're going to substitute in our sampling standard deviation. Let's just follow this same example that we did earlier. Before we calculated out the standard error of the mean, we knew that we knew our standard deviation of the population. It was 6. Now we don't know that value, so we have to estimate it. We still have 9 students that are in our small sample. So instead of using the standard deviation of the population, we're just going to use the estimate, which is the standard deviation of the sample. So the standard error of the mean now is the estimate of the standard error of the mean is going to be 9, our standard deviation of the sample, divided by the square root of 9, which is 9 divided by 3, which equals 3. So a slightly different value than before. But now, instead of conducting our hypothesis testing using known values for standard deviation, we're using it with the estimates that we have given our sample. Let's just go through the example for hypothesis testing, just so also as a recap for hypothesis testing. So we have a two-tailed test. We have a value we want to compare it to, a known value we're going to say of 29. Our null hypothesis says that the sample that we're going to collect is going to be equal to the null. It's going to be equal to this value of 29. Our alternative says, no, it's going to be different than that. We set our significance level again, alpha equals 0.05. This time, instead of going to the normal distribution, we have to make sure to select the correct t-distribution. For this case, we had 9 persons. We're going to take n minus 1. 9 minus 1 equals 8. So the degrees of freedom we would look up in a t-table, a table that we might use if we were getting into You have one in the back of your book, but we're not going to focus on those. But we might look up in our t-table values for our statistic that way. But also, this is our sampling statistic, and if you're doing this through the computer, it will automatically calculate this for you anyway. So we take our same value, we calculated a value of 34, that's our statistical value. We do the computation, now it's 34 minus 29 divided by 3. Remember, previously that was divided by 2, so we had a value of 2.5. Now, 5 divided by 3 is 1.67. We can go look that up, calculate that value, but now the p-value is 0.13, etc. It is greater than the alpha of 0.05, so the result this time is not significant. So our statistical significance level was not met, so we cannot reject the null hypothesis. We need to retain the null hypothesis in this example. We can just take the same example. We go back to the data, we go back to our population, we sample 9 persons, we end up calculating out a sample mean statistic of 38. And let's just keep the standard error that we calculated out constant. We'll just say we had the same standard deviation in the sample. Then we would have the value of 38 minus 29. 38 minus 29 divided by 3 equals 3. So it's 9 divided by 3 equals 3. And then we can go calculate that out. We would see that our p-value is smaller than 0.05, so our result would be significant. So now we would say, well, we reject the null hypothesis, and we would be able to go on to make some statements about the relationship between that this sample is different than what we expected in the population. Calculating at our confidence intervals is the exact same way that we did with our z-test, our hypothesis testing earlier. Now we'd have to go look up a table. It gets a little bit more complicated just because we have to know the appropriate degree of freedom. Knowing the degree of freedom tells us which distribution to look at to get our critical value. We're not going to go through this. There's a real simple example in your textbook, but computationally, it's doing the exact same thing. We're just going to look up our critical values based on a t statistic based on our t distribution instead of our normal distribution values. In this lecture, we're not going to touch deeply into analysis of variance, into regression analysis, or our parametric models. We're just going to talk about them at the very high level so we understand a little bit about them conceptually. Analysis of variance is like an extension of the t-test. We're going to test the null hypothesis that 2 or more parameter means are equal. We can test 2 means, 3 means. This just is now, instead of just being able to compare group 1 to group 2, we could have, like in some of our earlier designs that we were looking at, is maybe we have 2 treatments in a control group. We have 3 groups. We can use analysis of variance to examine the difference between those scores for the 2 treatments plus 1 control group. We can say, is there a difference amongst these groups? And to do so, we compute what we call a ratio of 2 variances. This ratio is a sampling distribution, and we call it the F distribution. It is defined just like a t-test is defined by degrees of freedom. Well, we have a set of degrees of freedom, 1 for the numerator of the ratio, 1 for the denominator. So each of our F distributions is determined by these 2 degrees of freedom, 1 for each of those variances. And there's a lot of types of analysis of variance. There is one-way analysis of variance, two-way analysis of variance. There's factorial analysis of variance. So let me go through a couple of these and give you the highlights of what they are. The one-way analysis of variance, we just have one independent variable. We have one dependent variable. The independent variable are our groups. We have treatment 1, treatment 2, and control group. We have one outcome. So let's put this in context of our healthy eating design. We have group 1, healthy eating, they eat apples. Group 2, we feed them chocolate. Group 3, they don't get anything. So we have 3 different groups. We look at our outcome measure of math achievement, and we would now use, instead of a t-test, if we only had 2 groups, now we have 3 groups, we can do analysis of variance. And it's a one-way ANOVA because we only have analysis of variance because we only have one independent variable. You can have more independent variables. If you have more independent variables, we call it a factorial ANOVA. If it were two specifically, we might call it a two-way ANOVA instead of a one-way ANOVA. But in general, when you have more than one independent variable that you're concerned with, you call it a factorial analysis of variance. So it gets a little more complicated with with two or more groups. So with just two groups, we would say there'd be effect due to the first independent variable. Maybe it's significant, maybe it's not. There could be an effect due to the second independent variable. Again, maybe it's significant, maybe it's not. And then we have an interaction where we take simultaneously the two independent variables and we see whether there's a difference or not. So just imagine we have our three groups as our first independent variable, and then let's just say we're going to try and also control for differences between male and female students. Then we would have a second independent variable for male and female students. So that could be an example of a two-way analysis of variance. We also have repeated measures analysis of variance. Repeated measures are when we test the same group multiple times. We test them one time, test them two times, test them three times. And we've seen that in some of our designs when we've gone through our quantitative research designs. We can also, and your book talks a little bit about analysis of covariance and COVA, where we add a covariate to those models. And maybe, we're not going to go into it, but there's also, if we had multiple dependent measures we wanted to use at the same time, there's multivariate analysis of variance. There are a lot of different forms of analysis of variance. We're really just going to focus in our readings on the one-way analysis of variance and maybe touch on just the two-way analysis of variance. But we're not going to go into depth in this video on it. We're just touching on it lightly, knowing that this is a test and knowing it follows the rules of our hypothesis testing. We can test the hypothesis of whether there's a difference amongst those groups, and we can use our logic, our same chain of reasoning to say, if there is a difference and the sample has been randomly sampled and the assumptions of the statistic are met, then we can chain back from the sample back to the population that we're interested in. We talked briefly about correlational analysis under descriptive statistics. So previously we talked about it just as a descriptive statistic, but now we can also conduct an inferential correlational analysis. This just means that we want to explore whether or not the correlations that we have are different than a value. Typically we explore whether or not the relationship between those two variables are independent of each other. So this involves testing hypothesis related to the correlation coefficient. We also see this in regression analysis, and I'll mention that in a moment. So this is probably, most frequently what we do in correlational analysis is we test the population mean is equal to 0. So we have a correlation, let's say 0.9, 0.7. We have some correlation, and we want to see in the population, our hypothesis would say that our null hypothesis would say there's no difference here. They're not, that these two things are actually equal to the correlation of these two things are equal to 0 in the population. Well, most of our variables, we would assume if they are independent, completely independent of each other, that our hypothesis is the null hypothesis would say these two things, they correlate 0, or within some sampling fluctuation very close to 0. So if there's no correlation between the variables, then our null hypothesis is supported. A statistically significant value would say that our value is larger than what we would expect in the population, larger than 0. So when we calculate a correlation of 0.9 and we go to test that, we would say that 0.9, if it is significant, that is different than 0. That's what we're saying when a correlation is significant. But I will tell you that this is so highly related to your sample size that when you get really, really, really large sample size, any correlation starts to become significant. So be cautious when doing some sample size, doing some statistical significance on correlations. We also use kind of standard ideas as correlation as effect size. So we say things like we have a small, medium, or large correlation in our sample, and we try to relate that back to the population. Multiple regression is another procedure related to our correlational techniques, and we're going to do prediction with it instead. So you have one or more predictor. Typically with multiple regression, we have multiple independent variables, and we want to use those independent variables, those predictors, to make a prediction about something, usually a dependent variable. So we're using multiple independent variables, one or more, and we can predict a single outcome, a single criterion variable. Some characteristics are that typically when you increase the number of predictors with additional variables, we get a better predictability. But you have to be cautious. You don't want to just throw everything in. You want to be very selective about those variables you're using as independent variables. Instead of talking about our correlations, we tend to talk now about our relationships between the independent variable and individual independent variable, and our dependent variable as regression coefficients. And we use a regression equation. We actually took a small peek at a regression equation in descriptive statistics. Let me just give you an example, probably a familiar one to many of us. Imagine you want to predict end of year GPA for incoming students to a university. So you want to predict freshmen's GPA. Well, this is what universities are typically doing when they're trying to determine whether to admit you to the university. So they build a regression model. They take things like either standardized scores like the ACT or ACT or the SAT scores. Maybe they don't at certain times. Maybe some schools have removed that from their prediction model. And they could also still use high school GPA. They could use a rank of your school. They could use measures of whether or not you did certain community service. They could do other measures that they can add in as an independent variable. They could even go through and rank or weigh your letters of recommendation. And they can build all of these things into a model, and they use those variables to predict something that really hasn't occurred yet. Your future, you're trying to predict what your freshman GPA is. Well, they do this based on existing data, right? So they take existing data, they take current students, they take their SAT scores, their high school GPA, other values they want to put into their model for predicting future incoming freshmen. And they build a model, and then after they've built that model, they now apply it to new students coming in. So that's kind of just an example of where one might use multiple regression. We're not going to get deep into the mathematics of multiple regression, but we just want to make sure that we have this as a highlight. Again, significance testing, understanding the effects of multiple regression. It's pretty much the same sort of logic again. We want to make sure that our predictors are meaningful, that they're large effects, that they're significant. We still can do hypothesis testing on each individual predictor, and we can still make those chain of reasoning. When we say a predictor is significant or a predictor is large, a predictor has a large effect size, a predictor has a significant impact, we can still do a chain of reasoning from the sample back to the population the same way we did with our t-tests and in hypothesis testing. Of our non-parametric tests, I just want to mention the chi-square test. We use our chi-square test, or as we use many of our non-parametric tests, when some of the assumptions of parametric tests fail, or, for example, with the chi-square test, when the measurement scale is not interval or greater. So this could be done with nominal categorical type data. We still want to have a test hypothesis about how well a sample distribution fits some theoretical or hypothesized distribution. So here with the chi-square test, we don't really have an assumption about shape of the distribution for the dependent variable. And the units we're using are not the mean in this analysis, but other statistics we use in non-parametric, like frequency testing. So in this case, the null hypothesis of no relationship is being tested. We want to know whether there's a relationship or not. And this is amongst our variables. It's kind of like we're doing a correlation somehow with categorical data instead. So in other words, this test is, we're testing whether or not proportions are compared to expected outcomes. So in chi-square test, we take observed portions and expected portions, and we're trying to determine whether or not they are the same or not. Here's our simple equation for a chi-square distribution for our chi-square test. At the heart of this test is the idea of observed frequencies minus expected frequencies. And let's just keep it at that. Let's keep some of our understanding at that level. If observed frequencies is equal to expected frequencies, then the O minus E will equal 0. We'd have no difference. Whereas the observed frequencies, as they are different from expected frequencies, as that value grows, it grows. If we see, we are actually taking that to the second power, so it grows even larger. So as observed deviates from what we would expect things to be, we end up finding significant values of chi-square. Here's just a really simple example. Imagine we're flipping a coin. We're flipping a coin over and over again. We flip it 100 times. Well, before we flip that coin, if I said to you, assuming that I'm not cheating somehow or that it's a normal coin, we'd expect there to be an equal split, 50-50 split. So if I flip 100 times, what we would expect to see if I flip that coin is that I flip the coin, it lands heads 50 times and tails 50 times. That's our expected value. Now, in reality, other things will happen. So in this case, I flipped heads 40 times and tails 60 times. So then I can do a little computation here. For example, with heads, observed minus expected, O minus E, 40 minus 50 is negative 10. You square that value, you get 100. Same thing with tails. Tails was 60 minus 50. I ended up having a difference of 10. And when we square that value, we end up with 100. So when we take 100 and we divide it by expected, remember expected here is 50, we end up with values of 2. We just sum those two things together and we end up with a chi-square of 4. It's not as much the computation that I'm worried about here. It's the concept here that we're taking actual observed data and what we expect that data to be, the frequency count we would expect to see for heads and tails, and we're seeing whether there's a difference or not, and then we can use that chi-square to test a difference. And again, I hope you see this theme, just like we do with any other type of statistical analysis. We can take that chi-square measure, we can test it upon what we have a sampling distribution, a known distribution of what those scores should be. We can say whether or not it exceeds those scores. We can then either retain, accept, or reject the null hypothesis, and then we can report that back as it might relate to the population. So we're still doing the same thing again as we would do with hypothesis testing. Also said I'd mention meta-analysis, and that's in our textbook. This is a technique, it's a statistical procedure for synthesizing results across many different studies. So you don't actually have to be the one to have conducted those original studies. You pick a topic area, maybe healthy eating. I go to the literature, I try to find every article I can, every reputable article on that topic area. And from each topic, I'm going to calculate out some effect size, some measure that they got to say how, whether or not they had not just significance, but how much of an effect did this paper demonstrate. So it's like an analysis of many analyses. You come up with a criteria, you come up with a rule for establishing which studies can be included into your analysis. And from there, for each paper, you're going to collect up one or more effect sizes, one or more impact of that study. You're going to pull them together, and then you're going to try and give a more generalized picture. After you have synthesized the results and conducted an analysis on previous analyses, you're going to give a general picture of what the effect was more globally. And we see this all the time. There's a lot of problems in research, whether or not an effect is more general. Well, this is one of the things we can do to determine whether or not there is a more global impact across many studies by pulling those studies together and trying to determine if we can see an effect across multiple studies. When we're considering the appropriate analysis, we can go through a step of several decisions. You have a nice little decision-making tree that helps out a little bit in your textbook, but there's also much better decision-making locations on websites I'll point you to in our Blackboard site. But when selecting appropriate analysis, let's just think through a few things. First, let's just think what the information that what do we want to do with the information we're gathering? First, are we doing just descriptive analysis, inferential analysis, or do we want both? Typically, when you're actually doing inferential statistics, you're also going to gather the descriptive statistics about them and report them in your study. So often when we're doing like even a t-test, we're still going to report things about the mean and the standard deviation. What are the level of measurement we're dealing with? And you should think about this not just for the dependent variable, even though that's probably the more important issue, but also for your independent variable. Do we have nominal, ordinal, interval, or ratio level data? What are the assumptions that will go into those measures that we're using? If we have interval or better data for our dependent variable, we're probably doing some parametric analysis. We also need to consider what assumptions are met, and that also relates to some of our measurement issues. So do we have the assumptions for a parametric analysis? Can we even conduct a non-parametric analysis? That is there a non-parametric statistic associated with the analysis I'd like to conduct? And then are we just doing a correlational study? And are we looking, even with that correlational study, are we going to do some sort of inferential analysis? So these are some of the things that we would consider around appropriate statistics. You also want to think about the structure of your method. We built a lot of different structures. That is, we focused a lot of times just on group differences, but we want to think, do we have two groups? If we just have two groups, or even if we just collect one sample, not a great design, but if we just want to collect one sample and compare it to a population value, are we doing a z-test or t-test? If we have two groups and we're comparing them to each other, what type of t-test are we doing? If we have multiple groups, multiple treatments in a control group, or just like 4 or 5 treatments, we have different groups. Are we going to do an analysis of variance? Do we repeat the measure over time? Then we have some form of repeated measures design. And we also want to make the determination of whether or not we want to do some form of prediction or not. So it could be a correlational type of study, but it could also be a prediction analysis where we're doing some sort of regression analysis or multiple regression analysis. So we want to think through the type of appropriate analysis. And again, you have some good resources, and I'll point you to some other resources online. In inferential statistics, we want to make sure, as we are considering other things besides significance testing and confidence intervals, that we don't forget practical significance and we don't forget about effect sizes. Effect sizes are just things like that there's a difference between two groups. Is it a large difference? Is it a small difference? Is it a medium difference? We want to make sure that when we think about significance, we also, as a researcher, as an expert in the work that we're doing, look for the practical importance. Results may be significant, but are they practically significant? So if we have a really large sample size, we may have a significant correlation, but maybe it's not meaningful. On the other hand, you may not have a significant effect, but as a researcher in the field, you might know that it might have a very meaningful impact on those that it is actually affecting. So we want to make sure to consider issues of practical significance, not just statistical significance. Also, we want to consider statistical power. This statistical power refers to the probability of rejecting the null hypothesis when it is indeed false. So are we able to detect differences between comparison groups? This could be, increased. We can always increase our statistical power. We have increased the sample size. The larger the sample, the more power we get. The more precise our variance measures are, the better our power is. And if we eliminate extraneous variables in our analysis, we get a better power. So statistical power really is their chance to find significance if it really is there. As we're sort of wrapping up some of this lecture on inference, I also want to just bring us back to the method section. A lot of what we're going to do with statistical analysis is we're going to conduct a statistic and we're going to report it in our results section. But let's not forget about our method section. So our method section has participants, who are the demographics, the people that are in our study, who they represent. We have a research design. We discuss our independent and dependent variable, how they should relate to each other. We have measures of our instrument, and we describe the instruments we want to use to collect data. Then, of course, we have procedures that describe data collection, but you also should include the statistical analysis in your method section. So our whole process should flow. In our introduction toward the end, we come up with a research question. We develop a more formal hypothesis. In the method section, we discuss issues around that hypothesis of the independent and dependent variable, and we put together a statistical analysis. And then in the results, we report the findings of the analysis. Just a few guidelines for APA guidance. I know you can look up a lot of APA style, but here's just a few a little bit of guidance for reporting results in your results section for APA guidance. Use past tense. When you report the results, you've already done the experiment. Be concise and objective. There is no reason to be wordy in the results section. That is fine. Once you get into your discussion, you can really add a lot of context, but in your results section, we're going to be very concise and objective. Provide all of the relevant information, and when you can, sometimes it'll go into the text that you're describing, but also when you can, provide tables and figures for people to understand your results. Things to avoid: don't explain the statistic. You do not explain a t-test in a results section. Do not include your raw data. That is not appropriate in a results section. And use tables or figures that you use. That's wonderful, but make sure you discuss them. Never use a table or figure that you're not going to discuss in your results section. So what should you report? I'm just going to describe what we should report for a t-test. It is very likely many of you are doing t-tests for your presentation. If you're not, I leave it to you to make, our hypotheses are really oriented toward t-tests. If you're doing something like ANOVA, I trust that we can extend this little bit of logic to analysis of variance, and you can use examples that you have gotten from your journals. But I feel it's helpful to walk through what we should report for a t-test because it does help us understand what we should report in general. So a statistic should follow from our hypothesis. So if we have a hypothesis, it should be, and we're using a t-test, it should be related to what our hypothesis was. We always want to report our descriptive statistics. We want to report means and standard deviations. Sometimes you will also report kurtosis and skew. For us, we'll just focus on our means and standard deviations. We want to report our test statistic. In this case, our test statistic would be a t-statistic because we're using a t-test. We would tell what degrees of freedom and the probability value that was used. So also, just as a note, in APA style, we round to 2 decimal places. So here we would say we did a t, that t there of 59. That 59 is degrees of freedom. That means we had 60 participants in our study for a two-group independent t-test. So we had 60 participants in our study. We had degrees of freedom of n-1. So our t of 59 was equal to 3.95. So they went through, they calculated out a t-value, and they're reporting it. And they tell you that the p, the probability of that 3.95, is equal to 0.031. That value is less than 0.05, so it would be significant. So you would talk about your results as if they were significant. Also note, when reporting statistics, this is more, our more general idea here is that non-Greek symbols are in italicus. So our M's are italicized and our T's are italicized. This is to draw attention that it's a value of a statistic, not just a reporting some sort of acronym or something. So here's 2 examples. You can use these examples and piggyback on them, adapting them for your own reporting of your presentation. So if I were doing a independent t-test, this is how I might report it. So I had graduate students, and then I was doing a little study on sleeping and working in graduate school. So graduate students who worked full-time had significantly less sleep. M, in this case, M is our mean, of 5.5 with a standard deviation SD equals 1. Now notice the M and the SD are italicized. They had significantly less sleep than graduate students who reported working less than full-time. Notice the M and SD again are italicized. M equals 7.5, the standard deviation equals 1.5. Look, those standard deviations aren't perfect, but they're close to each other. So talking about homogeneity of variance, that's kind of what we're looking for, that they're close to each other. If we saw a standard deviation in one of those groups as 1 and another one as 4, we would be suspect of those, whether or not they were equal to each other. And there are tests we can do to test the equality. We're not going to get into those now. So anyway, so we look at the mean here of 7.5 and the mean of 5.5. If you just look at the raw score difference, 7.5 hours of sleep versus 5.5 hours of sleep. Before I complete this piece here, I just want you to think of whether or not that is practically meaningful in your life. I know it would be in mine. I would love to get 7.5 hours of sleep. I often get 5.5 hours of sleep. So, but I'm also a parent of a 3-year-old right now. In my life, that would be a very practical significance regardless of the significance. So we also might talk about practical issues of getting less than 7 or 6 hours of sleep. We also see then we calculated out a T. It was an independent sample T. We have degrees of freedom of 58, which is related to our sample size. That T value, the actual T value we're reporting is 6.08, and we're just reporting that as less than 0.001. The only exception to their rule of reporting decimal places, sometimes we report to the 4th decimal place in APA style, especially when the p-value is so small that reporting it would be like 0.00001. So instead we just bring it back up to less than 0.001. The same structure holds for a dependent sample T. Students show a significant decrease on a nervousness scale. The mean equals 8.5, the standard deviation equals 2.0 after meeting with counselors. So before they met with counselors, their nervousness scale, they had an average of 8.5. After, they had a value of 7.6, standard deviation of 2. And that T for 29 degrees of freedom was equal to 2.46, which had an associated p-value of 0.02. This is just how we would report our descriptive statistics. So really, it's one sentence, but a lot has gotten into this one sentence. It's one sentence in this case for a t-test because it's relatively simple. In analysis of variance and regression, we may have a paragraph, we may have 2 paragraphs of data reported, but for us, especially for class, it is acceptable for each one of your research hypotheses that you develop. You're doing a simple comparison between 2 groups that you could just report something like an independent sample t-test. Independent sample is just like our treatment control as a reminder, and our dependent t-test would be as if we took one group, tested them with a pre-test and a post-test. There was a lot to unpack here. There's a lot more actually even in your chapters. Your chapters and your readings go a little bit more into analysis of variance and some of the computations there. But we focused on the background for inferential statistics and hypothesis testing and confidence intervals. So we should have taken away from here why we're doing inferential statistics with hypothesis testing and confidence intervals, how even though we sort of learned it under the structure of a normal distribution, of the sampling distribution of the mean, that hypothesis testing and confidence intervals, this testing philosophy is with every statistical analysis, even if you've never encountered it before. When someone says they've done a hypothesis test and they have statistical significance testing, they're doing the same thing, just maybe with a different statistic. So we learned a little bit about the structure of hypothesis testing. We also discussed another important issue we discussed was the logic, our critical thinking, coming to a conclusion from our statistic to our parameter to our population. So we used a chain of reasoning, random sampling, or believing that our sample is related to our population or reflects our population, all the way through our analysis back to the population itself. And then we highlighted some of our methods of analysis. Next up is simply a continued review of our 2 lectures, our descriptive statistic lecture set and our inferential statistics lecture set. So we're not going to have an additional topic, but we're going to continue to review the topics, the last 2 lectures, because there's a lot to unpack here. This one in particular is a relatively long lecture, so we're going to continue this topic into the following week as well.